everybody to this first ERDF seminar in the current 24-25 course. Today we have with us Christian Bebet, one of us, you know, member of the ERDF Institute since some months, I mean not even a year.
April 1st.
Okay, so about 6 months. So
yes.
I'm a member of our institute, but I'm sure that everybody know him already. Christian is a Ramón y Cajal fellow, in both in the mathematics department, if I'm not wrong.
Yes, in Leioa.
EHO, in the University of the Basque Country, and also in our institute, the ELCLI Institute. And, well, we'll give a talk today in our seminar. The title, A Short Tour in Model Theory. So, Christian, whenever you want.
Thank you, Karim. So thank you very much for having me. I'm very glad to try to explain a little bit where I come from. I will try to present a little bit of what is model theory, how it's connected to logic, and actually, yes, it's connected to logic and to mathematics. It's probably the branch of logic which is the most interacting with mathematics, although that can be debatable, but it's one of the more mathematical aspects of logic. And I'll try to present, yes, how, what are the essential components of what model theory is. And so first, let's recall what I mean by logic. Okay, so logic roughly is this sort of interplay. That's how I see it anyway. This interplay between the semantic and the syntax. So in the semantic side, you always start by existing things. For us, it will be this naive set theory, a sort of natural set theory, object, things that belong to each other, maybe just this as a basis, element, union of two objects. Okay, those are mathematical signs. I know some of you are not very connected to mathematics, most actually, I guess. But you are all connected to logic somehow. Okay. And so from this naive set theory, like the intuitive notion of sets and elements, you can construct what we call mathematical structures. A mathematical structure is given by a set and maybe some relations, some functions on this set, and some constant, some specific element that we specify. Okay, so that will be what I call the semantic side, and the syntax side is really first order or second order or higher order languages constructing strings of character that we want to put a meaning on. Okay, those are universal quantifier. This is for all x. There exists y, maybe some predicate saying something. Right, so those are strings of character a priori. You also have a whole system, very abstract system of having rule of deduction, like this famous modus ponens that everybody likes. This really belongs to the world of the syntax. And then at the core, at the intersection, the first intersection between those two is this notion of having a certain formula, a certain sentence, satisfied in a structure. I will give an example, but that's essentially the first time where the semantic and the syntax start interacting between each other. And then you have this famous theorem of Gödel that I just mentioned out of folklore, let's say. So this means that from a certain set of formulas, from certain axiom, I can deduce using my rules of deduction, I can make a proof of this other sentence. And this is a notion of deduction which is more related to semantic, which means whenever I have a structure in which this holds, then also it will hold, this other sentence will hold. Okay, so that's the semantical deduction and the formal deduction. Yes. And Gödel proved that for this first order logic, those two notions are equivalent. Okay. Actually, so Gödel 1930, there is a guy called Thoralf Skolem, maybe you know him, who actually had essentially the proof written down 10 years before, but he didn't maybe realize that was what he was doing. Okay, so logic, that will be my picture of logic. Maybe I have some remarks. This is young Kurt Gödel, handsome man. Okay, so the completeness theorem is a very interesting statement. In mathematics, it's not that often that we have such a statement. It's a for all statement equivalent to a there exists for statement, right? Because this means for every model, so a structure is this, and a model is just a structure. I will talk about the model of a theory. It's a structure that satisfies this theory. Okay. So this is a for all statement. It means for all structure, if this is true, then this is true. And this is, there exists a proof of this from this. And the fact that those two are equivalent is already a sign that it's somehow of a very deep theorem. And as a little gourmandise, there is a proof of Henkin of this theorem, which you can restate as if a set of formula is consistent, then it has a model. So what you need to do is construct a model, and he uses actually he uses the algebra of terms, which are essentially from some part of the syntax, some part of the language, to construct the model. So he really constructs a model out of purely syntactical element. It's a very beautiful proof. Henkin witnesses. Yeah, so you can say constructing the semantic from the syntax. It's nice to you can say it like this in a fancy dinner. It always look good. A little remark on set theory, which is a little bit schizophrenic, because so set theory is another branch, one could say, of logic, between logic and mathematics also. A little bit like model theory, but sort of parallel. And what they do is that they start with, similarly, we have this naive notion of sets, and then you can construct a first order theory, ZF, Zermelo-Frankel, which is just a little list of axioms, which gives you the behavior of sets, which we expect the set to satisfy. And then you discover a whole new world of new sets, which gives you insight on completely unpredicted new behavior with these new sets, which is at the same time a base, a foundation of mathematics for some people, but also this object, sometimes it seems it feels a little bit unnatural to consider this. I mean, they manifest very strange behavior. And even more so that a lot of mathematicians don't consider those sets to really, they try to avoid working too much with those because it's a little bit uncertain, and for deeper reasons that I will not mention now. But in model theory, we are completely fine with this Zermelo-Frankel approach of sets. Okay, it's just a side remark. Okay, so on the mathematics side, So we will only consider very basic things. So mathematics will not define mathematics, but essentially mathematics deals with number. You can have very, very complicated theorems, very complicated theories, very abstract objects, but in the end, you are just trying to understand the behavior of numbers. So numbers, those will be, this is natural numbers, so those ones, okay, that everybody knows. So 0, 1, 2, you can add them, you can compare them. 2 is less than 3. And so this, with the addition and with the order, is a mathematical structure on its own. One of those mathematical structures. Okay? And similarly, I will consider another structure like this, the line, the continuous line of numbers. It's called the real numbers. The abstraction is that you have a continuous line. Everywhere on the line there is a point which corresponds to a certain number. And again, you can add them, multiply them. Okay? And this is another structure, like R with addition and multiplication will be another structure. And we will consider essentially those two structures. There is also the complex number, which we'll mention a little bit, which is a little bit of a sort of generalized real numbers. It's a little bit bigger. It is a very important notion in mathematics. It seems a bit abstract, but in fact it is very natural in physics. People will use it all the time. It's a very convenient way of seeing a little generalization of numbers. And in this, so the complex numbers, C, every equation like this, or every sort of equation you can make, will always have a solution, if it's unconstant. A solution meaning a root of this polynomial. Does that, you recall from high school, right? You have a number, you change the x into this number, and you find 0, and that's the root of the polynomial. And you have these rules to find the root just by looking at the coefficient and things like this. But anyway, this field of complex number is just a sort of new world in which every polynomial equation will have a solution. That's essentially how it's constructed, in fact. But it doesn't really matter. The most important are those two very natural notions. Any question for now? Okay, so, right, so if you ask a biologist to define what is life, it's always very complicated because it's a bit blurry. The edges of coining the notion, it's very blurry. And I think we have the same problem in model theory. It's not always the case in math, but really in model theory we have problem identifying what it is. Yeah, right. People struggle finding an exact definition. Oh, yes. So I was listening on the way. Udi Ruszowski has a definition of model theory, which is the geometry of tame phenomenon, something like this, which nobody understands, of course. Yeah, I mean, there is a little bit of intuition behind it, but just when you have something very hard to define, you just use random words and hope that everybody agrees. Anyway, so here, one of the reasons why it's hard to define is because it interacts a lot with other branches of mathematics. We will actually see a little bit more on this at the end of the talk. Right, another reason is because some people are very opinionated, because some people think that this is model theory, and some people are very, very yeah, opinionated. I could not say it else. But anyway, everybody should agree on the following 3 points. So a model theorist will look at a certain structure through the prism of its definable set. So every time you have a structure like this, and you have a formula in the language of the structure, and this formula defines a subset of the tuples given by, so the set of all the solutions of the formula, of the element that satisfy the formula. This will be a definable set, and model theorists are just all the time trying to understand what those definable sets are. So if you consider the structure here, you can look at the graph of the function x goes to x squared, the famous parabola. Then it is a definable set. It's the pair of all the, maybe can I write here? Yes. So it's the pair of all a, b, such that b equal x squared. Okay, so it's, yeah. So this is the graph of the formula of the function, and it defines something in the plane which is definable. Okay, and this is a very crucial point, that model theorists will focus on the semantic rather than on the syntax. So it does not matter if a set is defined by one formula or another. The only important thing is what set it defines. The formula y equals x squared here, and the formula x1 squared minus x2 equals 0. Those are two equivalent formulas. I have changed the variables. I have just put a minus on the side, but it's on the other side of the equal. So those two a priori different formulas, they define the same set. And for model theorists, it doesn't matter. It doesn't matter which formula defines the set. The only important thing is that a fixed set, a set is definable, and that's enough. And then the third point is that model theorists study first-order theories by looking at their models. So there is a perfect correspondence between, at the same time, a given set of axioms, given set of properties, and the collection of all the structures that satisfy, that verify those axioms. And working only with this is the same thing as working only with T if you want to prove that a theory, I mean, this is a direct consequence of the completeness theorem. If you want to satisfy that a theory proves some theorem, then you look at models, you try to derive something, and then you go back. Okay, so on the model theory side, we'll rather work here. So that's a very modest, a more, yeah, it's sort of the same. The third point is sort of the same as the second point. Like it's a focus on the semantic rather than on the syntax, and that's why it interacts well with mathematics. Okay, so that's a funny picture of Tarski. It doesn't look so good. So Skolem maybe completed 1920. So those are the big names in model theory. Let's say the early names: Lowenheim, Pressburger, and then you have these two guys, Tarski and Robinson. Tarski is considered the father of model theory. I think he said it. He called himself that. A bit weird. But anyway, so what I'm going to do in the next two slides is I'm going to talk about what the early generation of model theories did in the 20th century. Okay, I mean, just a few examples. For instance, quantify elimination. Quantify elimination is a typical early time notion in model theory, and it really emphasized this sort of independence to semantic that model theorists are seeking. So independence to syntax, like focus on semantic. That should be the subtitle of my talk, actually. Okay, so a theory, so let's go through the definition together. A theory is quantified elimination if for all formula phi, okay, there exists another formula psi which does not use any quantifiers, okay, and such that the theory proves that those two formulas are equivalent. Let's rephrase. A theory has quantified elimination if every time I have a formula, there is another one which is equivalent, but this other one doesn't use quantifiers. So in a sense, so without quantifier, I will say a quantifier-free formula. And obviously, quantifier-free formula should be a little bit easier. And what is this saying is that actually here I want a theory in which any definable set is actually quantifier-free definable. Because now, because of my point here, if I have two formulas that define the same set, I don't care about the formulas, right? So I'd rather focus on just the quantifier-free one, and so I'm really working with quantifier-free formulas. Yes, and as a definition, a structure has quantifier elimination if the theory of M, or its axioms, has quantifier elimination. So let's see a concrete example. So let's first focus on the example rather than the remark. Okay, so maybe you remember from your early age, that right. Maybe I can do that. Can I have a? Who wants to solve this equation? Okay, this is -2 times -2. Yes, 4. It's 4, right? Yes. It's 4, and what happens to the 2 minus here? Well, they cancel somehow. I mean, they disappear. Why? Doesn't matter. Okay, so, and this is actually -2 squared. Okay, this is how we denote this. And you see, -2, this is, okay, 0, -1, -2, 1, 2. Those are the negative elements, right? But if I take a square here, then I always get, so -2 x goes to x squared, I always get a positive element, okay? So this is what this is saying. X is bigger than 0 if and only if there exists an element y such that x is a square. I didn't explain why it's an if and only if. It's an if and only if on the real line, but that's a way of characterizing positive elements. And what's happening here? Those two formulas are equivalent. One of them doesn't have quantifier, and this one has quantifiers. So this is the sort of phenomenon that I'm looking for. Okay, yeah. So in fact, this has quantifier elimination. So we just checked it for one formula, this one. It has a quantifier-free equivalent, but it's actually true that in here, any sort of formula, any theorem, any property you can express has a quantifier-free equivalent. And this has a geometric flavor, okay, that model theorists would prefer. Okay, the way to look at this is you have your parabol, which is the graph of the square function, and quantifying is actually equivalent to projecting. Okay, I'm not going to define exactly, but that's what's happening. And if you project this parabola to the axis, what this is saying is that this is quantifier-free again. And actually, the class of quantifier-free definable set is closed under projections is another way of stating quantifier elimination. Doesn't matter if you don't really understand what's happening here. The point is that what I did is that I rephrased a purely syntactical property into something which is more geometrical, more mathematical. Okay? Right, so, okay. What is this remark saying? This phenomenon, in fact, witness a default of expressibility or a collapse of semantic. That's again for fancy dinners. In a sense, there are no more definable sets than the ones defined without quantifiers. And this is exactly what's happening here. You have a whole system of constructing very complicated sentences by accumulating for all x, blah, 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 your quantifiers. And all this part, in fact, all those operators are unnecessary when the theory has this nice property of being quantifier-free. Right. So that's one classical model theoretic notion. Okay. Very old school. It's still very much used today. Yes, I have another remark. Yes. So it's a model theoretic property, so still quantifier elimination, model theoretic property that may happen for various reasons. Okay, so that's again a way of analyzing what this notion corresponds to. Here, so the complex number, the structure is very rich. So for instance, because having a root of a polynomial is always true, this sentence here is equivalent to the tautology, because it's always true. So that's another way of eliminating somehow quantification. The structure is very rich, it has points, it has a lot of witnesses, so I can eliminate the quantifier exists. And on the other side, if the structure is also very poor, it can witness this sort of quantifier elimination phenomenon. Here I gave you an example. So you take this line and you put a graph structure on it. What's a graph? It's a set of points. It's a cloud of points in which you decide to put relations or not. Just you say that those two are related or they are not related. Okay, so here I'm drawing a very easy graph. I take the natural numbers and I put an edge between two every time they are adjacent. So 2 and 3 are related, but not 2 and 4. Okay, I'm just saying, okay. And then I'm looking at this formula, which tells me, okay, there are two elements such that x is related to y, and x is related to y2, and y1 and y2 are distinct. Okay, whatever, it's a property, maybe. And this is true in this graph. For every point, you have two adjacent elements, except in 0, where you have only one. Okay, so this property, which is expressed using quantifiers, actually in this context can be simply rephrased as saying x is non-zero. That's another example. So the structure is very rigid, and that's why you can eliminate this formula. Okay, it's just another example. Still very much used today. Yes, it gives a nice description of definable sets. Quantifier-free definable sets are much easier to understand. Okay, and still today, model theorists always start. You start with a structure. You want to understand the definable set. If you can prove some sort of quantifier elimination, then you are getting closer to understanding how complex it is. Okay, so this is old school. Let's see, what time is it? Oh my God, okay. I have 1 hour?
Sort of, yeah, more.
Okay.
Yeah, it's okay.
Okay. So another very important notion in model theory, very classical one, is the compactness theorem. It follows from completeness, actually. It's very easy. Just if, okay, so it says if a certain set of axioms prove a certain property, then you only need a finite subset of axioms. Okay, like, yes, exactly. And why is that so? Because the completeness theorem tells you that it's equivalent, that this is equivalent to there is a proof of this from this. And the proof is by definition a finite object. Okay. It has a myriad of uses and applications. Yeah, some people would argue that its use defines model theory. Model theory is whenever you can apply this sort of strength statement. And it's true that for 100 years, people have found extremely different ways of using this very deep theorem in very various places. And so it's a very interesting phenomenon here. Okay, so you can use, for instance, that's a very early use of compactness is whether some property are exprimable using first order logic or not. And you can prove, for instance, that the concept of being of finite size is not first order axiomatizable. Okay, I'll give you the proof here, but let's try to advance a little bit more. Yeah, so that's another very classical tool. So I said, yeah, okay, the modern era. So this guy is called Sharon Shelar. He's a very nice guy, sort of. And in the 70s, he committed this book called Classification Theory. And he had a completely new approach for model theory, based on infinite combinatorics and more flexible constraints on structure. We'll try to get this very precise, or rather as precise as we can. Okay, so let's go back to our working example, so the line. I mentioned that it has quantified elimination. It's actually proved by Tarski. But if you forget about the order, so if you just consider plus n times, forget about that you have an order lying around. We do not have quantified elimination. Okay, because you can actually write this. This is equivalent to this. Okay, it's a little bit of what I was mentioning here. And so this nice property of having quantified elimination is not satisfied by this thing, which looks a bit easier than this. It has less expressible things, so there should be. Well, actually, they do define the same sets. They define the same sets. One has quantified elimination, the other has not. And it's a little bit problematic to have such a dependency to syntax. Again, model theorists, they have this idea that if it's too much depending on the syntax, we might be missing something. Okay, so quantified elimination is not, it's called preserved by interpretation, preserved under reduct. It doesn't pass very well from things that can be constructed from a theory that has quantified elimination. It's really sort of restricted and fixed, and we want some more flexibility. Right, so Shelar defined model theoretic properties which do not depend on the language. Those properties have a more semantic description via infinite combinatorics. I don't want to define this, but we will see what I mean here. Let's just see an example. Stability. The stability in model theory is very, very important notion. And here is how it's, so it's a little bit of a mouthful. It's a bit complicated, but we'll take our time. So a theory is stable if for all model of T, okay, for all formula in T, in the language of T, there is no infinite sequence of elements of M such that the following holds. I is less than J, so I have enumerated, so I've put it in bijection with the natural numbers, I have enumerated a certain infinite family of elements of M. And what I don't want is that I is less than J if and only if phi of AI, AJ holds in M. Okay, so for instance, we'll have here, we'll have, what do we know? So 0 is less than 1, so we'll have phi of A0, A1. Okay, and 0 is less than 2, so we also have A0, same thing avec A0, A2, but 0 is not greater than 1, so this one, sorry. So this is phi of A0, A2, but 0 is greater than 1. So I will have not phi of A1, A0. Okay, I have this sort of correspondence between this true statement, this sort of condition, which is a condition in the natural number, and I'm transferring it into the way that phi holds on this sort of line of elements. Okay, and this is a little bit more syntactic than semantic. Okay, so again, even if this is not, it's already a little bit semantic because I'm already in the model, but I want to get even away from the syntax by actually making it correspond to a purely semantic notion. So informally, no formula, so a theory is stable if no formula interprets, whatever that means, an order that behaves like this order here. Okay? And there is a persistence in those types of properties. So this is very important. Anything constructed out of a stable theory will again be stable, which was not the case for quantify elimination. Okay? Okay, there is an intuitive reason why it's a good idea to prevent infinite orders to exist. I will not get too much into this. I put this because, so you know, like radioactivity, if you have an object which is radioactive and then you take it, then your hand gets radioactive as well. And then you will shake the hand of somebody, it will also get radioactive. And so there is this sort of, those persistence of stability of these sort of notions. It gets transferred by touching somehow. Okay, so example, this is not stable. Well, I'm trying to prevent orders. So this has an order. It's a line with an order, so it's not stable. But this thing is, okay? It's not very complicated to prove, and it's a very archetypical example of a stable theory. This, right? That's a big one. Stability is an extremely successful notion in model theory. So it allows to generalize phenomena that occurs in C to many other structures only based on the fact that they are stable. Okay, so recall that a structure in model theory can be anything, from a graph, from line, from trees, orders. You can really take any quantifiable phenomenon in the world, and then surely you'll be able to modelize it with a structure. And what these properties, because those are properties of languages and formulas, so they apply to graphs and groups and all these sort of different things. And what it allows to do, having this very large notion, it allows to relate things that a priori are very, very different. So this is known as the world of algebraic geometry in mathematics. It's a very old and famous branch of mathematics. And why stability was so successful, it's because it was a very nice way of coining the nice behavior of this algebraic geometric thing, but being able to transfer it to anything which is stable. So not only on these sort of numbers, but also on some set of functions, or I don't know, graphs, or other contexts in which people were not expecting that there is similarity. Right. Make apparent link between a priori different structures. Right, so another point, it's maybe not the point, but another point is that, right, intuitive notion such that there is no underlying linear order. This is a sort of informal statement in mathematics. You don't want that much informality. But because you are working with logic and with languages and formulas, you can actually make this very precise. And that's where modular theory takes a lot of sense in mathematics, because you can use the formalism of logic to define intuitive phenomenon in mathematics and other things probably. This approach is at the core of model theory. Either look at the mathematical problems from the point of view of a logician, or treating logical objects with the eyes of a mathematician. Okay. Right. Okay. So let's have some fun. There are many other such, it's called tameness properties, with barbaric names, NIP, NTP2, whatever. The N stands for no blah blah blah, because you are preventing a phenomenon to exist. They constitute dividing lines in the spectrum of all mathematical structures, and so we can maybe have a look. This it's always a wait. Can I click this? It doesn't work. Okay, maybe I can just. This is weird. Okay, I'm just gonna go on the website, forking and dividing. You can see, right? Maybe like this. Okay, so what is this? What's this thing? So this is interactive. You can click. So this is sort of, it's called the map of the universe. It's a map of where each dot is a mathematical structure, and each area corresponds to a tameness property. Okay, so this is all the stable structures that we know, or most of the ones that we can describe. For instance, right, so this is, so you see there are like refined notions, strong minimality, DP minimality. So this is an IP here. So stable is sort of this quadrant. NIP is a little bit bigger. NTP2 is even bigger. And each dot, so here ACF, this is actually the complex numbers, the theory of the complex numbers. And this is, for instance, RCF, it's the theory of the real line. Okay, so it's not stable. I said it's not stable, but it's actually not too bad. NIP is a nice tameness property as well. And then you have fancy stuff. You have some things I don't even know. So this is generic binary. Yeah, okay. This is a sort of, yeah, this is bipartite graph. What's here? KN-free graph, okay. Anyway, there's a lot of universal graph omitting odd cycles of length, and why not? Okay, so people are trying to study definable set in these structures, and then they can prove that it belongs to a certain class of tameness. And so what's happening? It means that somehow two of these points, because they belong to the same class, they somehow, there is some combinatorial connection between them. Okay, and of course, those are very big, so very general. So it also means that they don't necessarily imply very strong constraint, whereas the very small ones, like strong minimality, implies much more connection, much more similarities. Again, between objects which might be very, very different. Okay. Where were we? Okay, so I think I'm almost done. So yeah, I had a few examples. Right. So most mathematicians work with, so, okay, so that's all for this. That's a very modern, or let's say in the last 30 years, strong aspect of model theory. And of course I talk about it because it's a lot of things I did is connected with this classification theory. Of course there are other things in model theory that I'm not talking about because I either don't know them or because we don't have time to cover everything. Okay, so maybe as almost concluding remarks, most mathematicians work with very powerful tools developed and adapt to answer precise questions using a certain amount of different structures. Model theorists have tools to deal with very wide range of structure at the same time, since everything is often stated in terms of formula in arbitrary language. Okay? The high level of generality associated to model theory is at the same time a strength and a weakness. So it's a strength because the results are very general. And very general, so it allows to uncover new connections between mathematical objects. But also it's a weakness because the more general a theorem is, the weakest it is, the less powerful, the less important thing it's saying, almost by definition. So finding the right degree of generality is often the very hard part. Right, so general tools are weak when applied in particular examples. Often this means that the tools are to be refined in order to yield stronger results. All right, so let's see, let's dig a little bit more in this idea. This has a perverse effect, resulting in the partitioning of model theory in various areas becoming more and more distant from each other. A recurrent pattern is the following. First, a new area emerges, a new connection between a mathematical question and model theory. Okay. Then the tools of model theory are applied. Model theorists are like, okay, let's do that. We can apply this theorem, good. But then, because the theorems are very general, then there are more specificities that you don't see in particular mathematical questions. So the tools get more and more specific and adapted to this new area, which then does not rely on model theory anymore or that much. There is sometimes a retroactive loop. Specific tools can also be generalized to the model theoretic framework. This is also very, very interesting, very powerful. When this happens, it's often the most important results of model theory come from this. You actually start with a particular example and you uncover something that you can generalize to a model theoretic context. Okay, so this is all this is my limit with LaTeX. I couldn't do that on LaTeX. So I even asked ChatGPT to do it, to change this into LaTeX. It was a disaster. Okay, so this is just a picture to illustrate this idea. Model theory is like this platform where new topics enter, and then you apply the tools, and then you make a new branch, like minimality. Maybe it doesn't mean that much for you, but if you ask, it's a very successful application of model theory to actually the real line. It's like the model theory of the real line somehow. But now if you ask a mathematician, a random mathematician, he might know about minimality without knowing about model theory. Okay? And this is also true for other examples, motivic integration and blah, blah, blah. Non-standard analysis. Okay. Okay, so in conclusion, model theory is a branch of logic and a branch of mathematics. That's how I see it anyway. It focuses on mathematical questions with the point of view of logicians. Okay, so with the background of having theories, definable sets, formulas. And it also focuses on logical questions with the approach of mathematicians. So that's the more semantic way, like, okay, this is a complex syntax property. Can we see it geometrically? Can we do something? Can we use the approach of mathematicians to understand that? Okay, so I think that's all for me.
Okay, so time for questions, comments.
Okay, I'm good on time.
I have many questions.
Go on.
Can I start? Yeah, first of all, it was like nostalgic for me. When I was an undergraduate student studying, I mean, we learned many things about Robinson and Shell.
I see.
Yeah.
Okay.
Philosophy studies. So
Yes.
a long time ago, it was fun to read them. Now I forgot everything, of course. So I just first a very general question. How standard is the view you presented on model theory? I mean, how is representative of model theory really is? Like in the sense that it happens with logic, right? But that for some of us, I mean, logic means first order predicate logic, and then there are many more.
Yes, yes.
But they are all based on the big font, whatever.
Yeah.
The roots are first order logic, right?
Yes.
Logic. And the other are extensions or deviations or whatever.
Mm.
And there are lots of people working on them, but still, when you present logic, as you did, right?
Yeah,
it's
yeah.
First order. But then we know that for linguists, that's not their logic.
Right.
They need intentional higher order logics and stuff like that.
Yeah.
For other people. So many people would say that nowadays presenting logic as if it were first order predicate logic is too reductive.
Yeah.
Doesn't represent what people are really doing,
Mm.
right? Because first order logic is already done. We
Yes.
know everything about it. We have all their properties now, all that. So that's my question.
Yes. So
Is there model theory that is
yes. So
non-extensional or dealing with non-well-founded sets?
So the
I mean, things like that.
yes. So there are various things that actually I had a slide with a list of all the things that I either don't know or don't have time to mention. Among them, there are a bunch of different logical systems that model theorists use. But, so for instance, you have this sort of continuous logic in which instead of having a Boolean value for truth or false, you have a continuum one. It goes into the segment 0, 1, so it's maybe 1/2 true or maybe 1/3 or something like this. This had, so this approach exists. It was actually developed by different people with different sort of settings. There is one today called continuous logic or continuous model theory, which is very active. There are older ones that have been forgotten. I think Pfefferman was one, developed one that didn't really work. But it's also, so there are other systems. There is also positive logic where you don't use the negation and you start trying to see whether you can do a little bit of model theory with it. And this is working okay. To my taste, I think it still has to prove that it leads to really interesting things, but it has been developed now maybe for 15 years, something like this. I even have a paper in this setting, in this positive logic. So, and there are many other examples of this. And because it's always the same thing, because of this last line, this last slide, when you reach, like when an area is almost about to leave somehow model theory, then the reaction can be, okay, maybe we can modify a little bit our setting so that it corresponds more to this. That's exactly where continuous logic were invented, because first order logic is somehow discrete, and they wanted a continuous version of this to study examples in mathematics, which are like functional analysis, things that doesn't quite fit well with first order logic. So yes, so there are a lot of this, but there is another thing to take into consideration, and it's a little bit connected to this compactness theorem, because a lot of things are connected. A lot of the approach is connected to this compactness theorem. People either try to describe the logic in which, the best logic in which you still have compactness, or you will try to weaken a little bit the compactness theorem, working, a little bit, try to play on this factor. And there is a theorem, I think of maybe Lowenheim, that says that first order logic is the only logic in which you have at the same time compactness and Lowenheim's column theorem, or something like this. You have this sort of statement where people really want to optimize. At the same time, I want to keep the tools I have, compactness, and I want to extend my setting. And they try to play a bit on this. So yes, other logic systems, yes, they use it. Although, you see, working with first order logic here for mathematical questions, it might seem as a restriction, but the way we use it is that, on the contrary, because you restrict yourself to this definable set, which is a class of, it's not a very big class of set, it's a big class of set, but you don't capture everything. But the tools we use to manipulate definable sets are completely out of first order logic, right? They are like the mathematicians' bread and butter. So axiom of choice, yes. Excluded middle, what is it? Excluded, yeah. You use everything. You're not restricting your mental tools. You're just studying any object with this little prism, with these little glasses of first order definable sets. So yeah, often it's a bit funny because first order logic is somehow, it was a very nice setting to get foundations, right? To try to understand foundations of mathematics, foundations of this. And the idea is that you restrict, you cannot say anything, you don't want this sort of paradox, you restrict it. And then you can see that some of the tools you're using are not part of the first order thing. You restrict, but model theory is not doing that. The restriction is only, how to say, you're still using everything. You are using all the worst nightmares of church and the constructive people, the people that wanted constructive mathematics. We are using their worst nightmare every day. It's based on the axiom of choice in this stronger form, and so yeah, the restriction happens only on what we study, but how we study it, it's open bar. I don't know if that answers your question, Kepa.
So you still see that this is like the core of contemporary model theory?
Yes, so it's not the core. I think classification is yes, sorry. So the Sheila stuff, like the map, and this is called classification theory. I wouldn't say it's the core, but I would say it's a very, very big part, and sort of the most it had in the last 30 years various successes, but I wouldn't say it's the core part of. It's maybe the most abstract part, in the sense not connected to other, not directly connected by itself to other mathematical branches, although it does connect, but its stability is studied as a property, as a logical property of theories. So it's probably okay, maybe I can say that. It's probably the most important abstract model theory discipline. Okay, but if people, right, but a lot of model theorists are actually almost mathematicians, in the sense that they focus on, I don't know, the complex numbers and its definable sets, or yeah.
This might be a very stupid question because I know nothing about logic, but you were talking about this quantifier elimination.
Yes.
And I was wondering if something gets lost when you have like two formulas, one with the quantifiers and another one without, because you were giving some example with these adjacent numbers.
Yes.
And it was reduced to x is different from 0 or something like that.
Yes, yes.
And from an external point of view, it seems that the formula was not saying only that, or that there was something that were lost.
I think it's a very interesting point. Again, because of the philosophy, we only look at definable sets and not at the formula. Then you lose this difference between what this is exactly saying and what this is saying. Okay, we completely ignore this sort of which in many other branches, even in other branches of mathematical logic, they would consider this as a different formula. Maybe if they want to, I don't know, implement algorithm that will manipulate the formulas, of course, they will see this as a completely different formula from this one. But for us, because of the sort of geometric aspect, I want to look at only what's happening here, right? What's happening on the line. This formula, it's a formula with free variable x, and it picks out of this line one definable set. This formula picks out one definable set, and it turns out those are the same. And so the geometry of definable sets, we'll only see this. But it's not, in a sense, it's not part of our mental approach to consider this as a different, to look at its meaning, actually. We don't care about the meaning of the formula. Because it's more it's easier to just look at the definable set, and so we can have somehow stronger results because we don't make these differences. But no, we don't. So the choice is that because we consider formulas up to elementary equivalence. Okay, so two formulas which are equivalent, we consider they are the same. This allows to have stronger results because we are dealing with less complicated objects. It's a choice. I think if you do lambda calculus or some other branches which will look more at the syntax, then of course you can't do that. And you'll get other sort of results, maybe harder to get and answering other sort of questions.
So I was curious to know how does your own work specifically fit into, because you gave like a,
Yes.
a map of model theory. Right?
Ah, I can show you.
How does your own work fit into?
Yes. Okay, I don't know which one. I proved one of these is here. One of these is mine, I think. Maybe this one, I don't know. One of these in DP minimal. Yeah, two actually in this. One here. Here I have a bunch. Yes, I did a little bit of this game.
Seems like you discovered and
So, yeah, so how does it work is that you, there are very interesting questions on this map. For instance, if you look, you see here, there is nothing in here, NSOP3. There's nothing, and it's actually open. So NSOP3 and NSOP4 are defined differently, okay? One has a dependence to 3, the other one has a dependence to 4 in its definition. But we don't know an example of something which is NSOP4 and not NSOP3. No, yes, exactly. So what's happening here is that we don't know if it's a definition à la Shelar, the same thing as the order, but with another more complicated object on the semantic side. And those definitions are sometimes so abstract that we don't have examples of things which really cut them out. Okay, so this is the case for NSOP3, and it was long open whether NSOP1 and NSOP2, okay, you can't see, but NSOP1 and NSOP2, it was long open whether those two things are the same. And it was proved 2 years ago by a young guy from the US. A long conjecture, and it's true, those are the same. So it's very strange, and here nobody knows what to expect. Is NSOP3 equal to NSOP2 and NSOP1, or is it equal to NSOP4? And so how you deal with this? Either you prove abstractly that those two things are the same, or you find an example which fits here, which is not here. So yeah, and so a lot of people try to construct complicated example or to look at classical objects and try to see where they fit. And this is not only to separate the classes, this is a bit anecdotic. The most important part is that once you've proved that, I don't know, something is stable, then you have all the power of stability theory that you can apply. And yeah.
Just a follow-up, just to understand that. So, because you mentioned the star thing, the universe and all that, right? So it's like...
the star, which star?
It looks like the point...
Yes, stars. Yes. Yes, it's true.
So my question is like, do you have, or do you consider that the inventarium of existing mathematical structures is already set?
No.
And they're not new, stars coming out.
No, look.
Right now,
We are very organized. Look, if we look here, where is it? I don't know. Reset maybe. Yes, open regions. So those are opens, okay, and open examples. There are a few examples. Okay, it's not up to date, but yeah, there are a few objects that we don't know where it fits at all.
where it is.
Exactly. And this one, for instance, the C of t, this thing, is a very classical object in mathematics. It's a very natural object. Yeah. And so people think that it might be stable, which is, it's one of the biggest conjecture we have, It might be stable, it might not be, we don't know. If it is stable, then it contradicts another conjecture of Shellard that says that something else.
So there are
So
structure that you don't know yet
where it fits.
where to sit with, right?
Yes.
But there are, things that can appear, new stars in the universe.
Yes.
I mean, because somebody invents. I mean,
Actually,
it's still not open to invention.
yeah. There are many. Like for instance, the groups are very classical object in math. They correspond to symmetries of objects. They are omnipresent everywhere. Every mathematician uses groups. And groups, we know, for instance, that they can be anywhere. There are some sort of groups that are here, some sort of group that are here, some that are here, some that are here. We already know that. We can prove this. But there are also very specific groups for which we have no idea, which are very complicated to understand.
But then it sounds like you know which groups there are there. The thing is that you don't know what to put in the image.
So it's, okay, maybe our problem here is that group is a very, very wide notion. So it's sort of a bit silly to consider the question, where does group fit in this thing? Because there are as many groups as you can think of. And there are two sort of examples. I should have mentioned this. You could say there are two sort of examples. There are examples that are constructed by model theorists to appear on the map and to create phenomena so that we can see phenomena appearing. And there are mathematical objects that mathematicians use and that are that have their own interests somehow, and then it's very important to be sure to understand where they fit here. This is the sort of example. Those two examples are Timbrate group as well. Those are objects which are known to be a bit complex for mathematicians. And it would be very nice to be able to know where they fit. This would also help mathematicians because of course, stability is not just a funny square on a plane. Stability is you have books that tells you that in stable theories there is this phenomenon always, there is this always, there is this. So when you find a theory is stable, it's not to put it on the map, it's to apply the tools that will allow you to decorticate the structure of it. But yeah, there are room for many, many more examples. Sorry.
Yeah, it's not a main question, but just to push a little bit further the analogy with astronomy.
Yes.
When you mentioned that there are so many spaces waiting for some new models or historic.
Yes.
It's actually something that has been common in astronomy, where the weird behavior of the planets suggested that in this space there would be something, and all the astronomers were looking in this space.
Yeah.
But this is not the question.
No, but
This is not the astronomic analogy. There is something there.
Yeah.
But the question actually is a very general one, maybe even in general in philosophy of mathematics or something like that. You mentioned at the beginning that there seems to be some kind of disagreement on how mathematicians react or take set theory, or how friendly they are to set theory and so on. And at first I was thinking about the possible criteria they have for having one or another attitude towards set theory, and then I was thinking that in epistemology there is an interesting topic on disagreement and on reasonable disagreement, and there seems to be some paradox there to be explained on whether it is possible to disagree with someone when you share all the information and at the same time you still hold your belief which is the opposite
Mm.
with the one held by the other party in the disagreement, and you still think that the other one is rational. So how can it be that if you share all the evidence, you still think that you have enough evidence, you know, to still hold your belief while thinking that the other person, while, you know, holding a different belief, is rational? Some people suggest that reasonable disagreement is not possible, and I was thinking, in general, in mathematics and in these sort of formal fields, it seems almost, you know, even more difficult to have these sort of reasonable disagreements, because it seems easier to, you know, to identify when you share all the evidence. I expect that when two mathematicians have very different attitudes towards set theory and believe different things about set theory, I expect that it is not that difficult for them to put together all the information they have to have.
Right. Okay. So this is a very deep topic, I think. But I would say I've been thinking a lot about this because, I mean, I'm a model theorist. We are confronted to this question since the beginning of your study of model theory. You do model theory and set theory most of the time now. You do both at the same time, and then you discover a completely new field of knowledge that seems almost absent from the mathematical landscape, set theory. So I would say that the main reason for mathematicians to believe or not in set theory is pragmatic, is whether the tools from set theory can be meaningful to your field of research or not. Everybody agrees that the theorem of Cohen, the theorems in set theory are true. Nobody thinks that the theorems are false in set theory. Nobody thinks that set theorists are doing crazy things on their own. I mean, yeah, people think that. But it's not about whether it's true or false. It's about whether you can use it or not. Because I think people now really know what the theorems of independence say in set theory. What it says is that you can put yourself in a universe in which the axiom of choice is true, for instance, and so if I need the axiom of choice, I'll consider that, okay, I'll just put myself in this situation. Because we know that it's independent from our basic intuition on sets and on numbers. That's the conclusion of the 20th century mathematical logic, is that it's not inconsistent to have all these fancy objects lying around, inaccessible cardinals, these sort of things. If you need them, well, why not? I'll work with them. So some people then will say, okay, some people will say, no, this is too crazy. But anyway, most of the mathematicians don't actually need the most crazy things from set theory. They only need sometimes a little bit of axiom of choice. So they say, okay, just take a maximal ideal in your ring, and this is actually an application of the axiom of choice. But they will sort of go quickly on it. There are other sort of, but yes, I mean, as long as we don't find any contradiction in mathematics, then we consider that we can do the mathematics. There are other phenomena that are a bit like this, and now it's not even about whether the theory is undecidable or whether something is complete or whether we can know or not. It's it's even more pragmatic. There are theorems in math that they are just too hard to double check many times. There is something, for instance, called the classification of finite simple groups. I don't know if you know. Classification of finite simple groups. It's an enormous amount of work of generations of mathematicians. And in the end, you have like a big theorem. You have a book that consists in the statement of the theorem. And the proof corresponds to thousands of pages of work that nobody can comprehend in one go. So, and this classification is crucial because it's very important. It's all the finite simple groups. Can you imagine? So, how do mathematicians react to this? They would say, so this is my theorem, and in parentheses they would say it uses the classification of finite simple group. You will keep track that you are using this very, very hard theorem that today nobody knows the proof of the whole thing because it's too much work. You could have you could ask a PhD and ruin his life to write a correct proof of this theorem. I am not sure in 4 years he can actually do that, even just compiling all the existing papers. So, so the phenomenon we are facing is no longer about it's like physically, sorry, it's physically difficult. It's physically, like, I mean, in the physical world, it's too much paper. It's too much for my mind. So I'm having this sort of yes, I believe in the classification of finite simple group. And so, to be sure, how we deal with it now, it's really that. We always mention if the theorem uses the classification of finite simple group, you will say it. And so everybody knows what it means. It means, okay, this theorem holds with the classification of finite simple groups. And what people then will try to do is that find another proof which doesn't use the classification of finite simple group. So the effect is like, instead of having an amazing theorem offered to the community, it's so hard that people prefer, okay, maybe if we find another proof that doesn't use it, it's better, to be sure. So, and people do the same with like the intuitionistic mathematicians. They wanted to reprove everything without using the excluded middle. Yeah, I don't know. Sorry, I went into a monologue, so I don't know. Did I answer a little bit to your question?
No, more or less.
Any more questions? Yeah. So maybe related to your question, there is like the topic that like not only like in set theory, there are people that say not only that there can be that are not useful for their own research topic, but that there are in the end not useful in any useful research topic. So
yes.
Like additively where Pfefferman goes, and so maybe for it is in this sense that like this disagreement could come, but well, there are more a lot of stuff to talk about that topic.
Yeah.
But my question was. In the equivalence between structures and theories in the first moment, I think, and I would like you to hear your opinion on that, that there could be kind of a circularity, because you understand a structure and you ask what is a structure, and sometimes the answer in the practice is, well, a set, or anything that does follow from the theory, but then you need a theory, and then this structure applies to the theory, and then which is the primitive concept there, or what can happen there?
You mean between structures and theory, or between structures and set theory, and
exactly. So
because of the naive set theory thing, right?
So a structure has to be defined in terms of you
existing things.
would like to define it in terms of set theory, but
Yes, but you cannot do that.
you can exactly. So
Yeah,
the structure is a primitive notion in the end.
Yes, yes, yeah, I agree. And actually, yeah, I think that's really, I think, yeah, I mean, I think you said it all, right? You need a sort of naive set theory. Maybe the only thing, okay, you can be more precise on what you need. Maybe you only need these things. Actually, you can sort of do everything with this, more or less. Once you have sets and maybe sequences, you can more or less do everything starting from this. But yeah, so you need this. So yeah, structures are very primitive notions.
But in
Yeah.
practice, you usually use Zermelo-Frenkel theory to define a structure.
No, so the thing is, maybe this is the remark you want me to comment on?
Yeah.
Yes, so yeah, so here it's really about, it's not about foundational of our basic object. It is about it is about the tools we use as mathematicians trying to understand the combinatorics. So for instance, it's because we want to have the dependence on the independence on the model. We want to be able to go in higher models. So first you'll have cardinality properties to deal with. And then because you have cardinals, even if you have naive cardinal notions, there will be arguments that you can only do doing a transfinite induction. So you will need your ordinals as well. And then slowly you'll use infinite combinatorics a lot. Yes, I didn't mention this. Like infinity is always present okay. There is something called finite model theory, which is very different from what I presented here today, which I don't know much about, to be honest. But for us, structure will always be infinite for some reasons. And so you will have to deal with a lot of infinite combinatorics, meaning considering how do you define combinatorics? I don't know. Yeah, infinite sets and the way they relate to each other. I don't know. Sorry. So yes, so a lot of it's not ZF for its foundational aspect that we need. It's ZF for the tool that they actually define.
Yeah.
Ordinals, cardinals, all the cardinal arithmetic, this sort of things is used a lot.
So
but
you don't know what is exactly a structure, but you know that what is true in CF is true for a structure, so you get along
yes.
with that.
Yes. And sometimes you are, yeah, actually there are, I could list a few proofs that that users that need you to put you in a universe where a continuum hypothesis works, for instance. You know, like these things. So yes, there is a good permeability between model theory and set theory. Not necessarily for a foundational aspect, but because set theory actually brings a lot of tools. It brings a lot of, yeah. And also we are influenced by this guy Scheller, which is a set theorist also.
Yeah.
So he phrases a lot of things in terms of set theory. And then it's the work of some other people to try to get rid of as much set theory to have cleaner. But yeah, set theory is more like a tool,
Yeah.
than a foundational question in model theory.
much, Christian.
Thank you.